Hello, this section's 4.1, scatter diagrams and coloration. All right, so first of all, we need to talk about the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. So the response variable you can treat as y, and then the explanatory or predictor variable as x. So the scatter diagram is a graph that shows a relationship between the two quantitative variables measured on the same individual. So each individual of the data set is represented by the point in the scatter diagram. So explanatory variable is plotted on the horizontal axis, and then the response variable is plotted on the vertical axis. So example 1, we are drawing and interpreting the scatter diagram. So data shown on the right are the base of the study of the drilling rock. The researcher wanted to determine whether the time it takes to drill a distance of 5 feet in a rock increases with the depth of the at which the drilling begins. So the depth at which drilling begins is the explanatory variable x, and then time, the minute to drill 5 feet is the response, the variable y. So the draw or scatter diagram of the data. So I have x value here, y value here. So x value as a distance, which is a depth, and then the y is the time, which is a minute. So I already have a table for you. So the scatter plot, that when you plot it in, it comes out this, okay? So 35 takes 5.58 minutes, and 50, 5.99, and 75, 6.71, 95 is about here. So this is what I plot them in from the previous table. And then we have a various type of the relation in a scatter diagram. So the explanatory and the response coming to this way, we call the linear. And then the negative way, we still the linear as a line. And also this is actually not a line because it makes looks like a parabola. So we just need to say non-linear. Also, this doesn't make any straight line, so non-linear case. And this is actually the no relation at all. So two variables are linearly related, positive associated when above the average value of the one variable are associated with the above the average value of the other variable. And below average value, one variable are associated with the below average value of the other variable. So that is the two variables are positively associated if whenever the value one variable increases, and then the other value also increases. So that's what we call the positively associated. So let's look at that. And two variables are linearly related positively associated with the above the average value of the value associated with the above the average value of the other variable. Average values of the one variable and associated with the below average value of the other variable. So there is a two variables are positively associated if the whenever the one variable increases and then the other ones also increases. Actually kind of repeated from the other. So the linear correlation coefficient or Pearson product moment correlation coefficient is a measure of the strength and then directions of the linear relation between the two quantitative variable. So we use the Greek letter rho represent the population correlation coefficient. The R that represent the sample correlation coefficient. So we present only the formula for the sample correlation coefficient. So sample linear correlation coefficient R, and then sigma sub up, and then x sub y, and then subtract the mean of each of the variable, and divide by standard deviation of each, and then divide by n minus 1. So x bar is the sample mean of the explanatory variable. X sub x is the sample standard deviation of the explanatory variable. Y bar is the sample mean of the response variable. X sub y, S sub y is the sample standard deviation of the response variable, and it's the number of the individual in the sample. So property of the linear correlation coefficient. The linear correlation coefficient is always between -1 and 1. So which is, we can put it this way. And then if the R is a positive one, that means a perfect positive linear relation. And the R is a -1 is a perfect negative linear relation. And then the R is close to 1. And then the strong evidence of the positive association between the two variables. And then R is close to -1 is a strong evidence of the negative association between the two variables. And the R is close to 0. That means no evidence exists of the linear relation between the two variables. So R close to 0 does not imply no relation, no linear relation. All right, let's look at the next page. And 7, linear correlation coefficient is a unitless measure of the association. So the unit of the measure for x and y plays no role in the interpretation of R. And then so there's no the unitless measurement of the association. So number 8, the correlation coefficient is not resistant. Therefore, the observation that does not follow the overall pattern of the data could after the value of the linear correlation coefficients. So the first case is a perfect positive linear relation. And then this is getting close to 1, so strong positive linear relation. And then this is about the R equal to 0.4, which is a moderate positive linear relation. And this is a perfect negative relation, linear relation. Strong negative linear relation, and then moderate negative negative linear relation. And this is actually everywhere, right? So no linear relation, and this also the not as a line, so non-linear relation. So yeah, so this is kind of see as a data here. All right, so now to determine the linear correlation coefficients, so we need to actually find out what we can actually compute this is a table. Okay, so we need to fill this. So determine the linear correlation coefficient. We need to have x bar. We need to need a y bar, s of x, and then s of y. So in order to find the x bar, you just need to adding all the depth of x's together, and then divide by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So divide by 12. And then when you do that, I got 126.25. For the y bar, which means you adding all the y value together and then divide by 2, which is what I got is 6.985833. For the x sub s is a standard deviation for the depth, which means there's a formula though, right? Hopefully you remember that too. So which is s equal to square root of sigma x sub I square and minus sigma x sub I square over n minus 1, right? So if you plug it in for x, and then you also need to plug it in on y, and then you get as 50. You can use a calculator too, okay? So 52.22874, and then s of y is 0.780774. Okay, now once you got this, and then for the first one, so as this expression, so x of y is, this is all x of y here, this is, okay? So you can just put it as a 35, subtract x bar, which is 126.25, and then just divide by x of x, which is a 52.22874. So you can use calculator, okay? For the second one, yi is the 5.88, and subtract y bar was 6.985833 over x of y is 0.780774. And then what I do is, whatever value you got from this, you plug it in here. And whatever expression you got, you plug it in here. And then multiply, that'll be that one. So that's how you finish all the table. So actually, I already did it for you on the next page. Okay, so this is what I got from the, and then once you got, and then we need to actually use the formulas of the linear coloration coefficient R, and then using the sigma sub, which means you need to add the once you got this, and then you need to get you need to add them all together, right? Which is this is the value of this one, right? So when you add them all this together, and then you get this one, and then divide by n minus 1, so which is n is a 12 minus 1, and then this is r equal to 0.778, which is I want to say this is a moderate the positive linear relation. Okay, so testing for the linear relation, determine the absolute value of the coloration coefficient and find the critical value of the table 2 for the given sample size. If the absolute value of the coloration coefficient is greater than the critical value, we say the linear relation exists between the two variables. Otherwise, no linear relation exists. All right, and then example 3, does a linear relation exist? Determine whether the linear relation exists between the time to drill 5 feet and the depth at which the drilling begins. Comment on the type of the relation that appears to exist between the time to drill 5 feet and depth at which drilling begins. So I have to say that the correlation between drilling depth and time drill is, this is r equal to 0.773, and then the critical value that you can use from the table 2, which is you can see below there, for n equal to 12 observation is, okay, so let's find here. So n equal to 12, which is this number, so 0.576. So now you need to compare with the 0.773 compared with the 0.576, but 0.773 is the greater than 0.5776. Now you can say there is a positive linear relation between time to drill 5 feet and depth at drilling and begins. Okay, all right. All right, the looking variable. Another way to that the two variables can be related even though that there is non-causal relation is through the looking variable. So looking variable is related to both explanatory and response variable. So for example, ice cream sales at crime rate have the very high correlation. Does this mean that the local government should shut down all the ice cream shop? No. Looking variable is temperature. So as air temperature rise and both ice cream sales and the crime rate rise. So like a temperature, we call that as a looking variable. Okay, so looking variable in bone mineral density study, because cola tends to replace healthier beverage, and cola contain caffeine and phosphoric acid. Researcher Catherine L. Tucker and associates wanted to know whether the cola consumption is associated with a lower bone mineral density in women. The table lists the typical number of the can of the cola consumed in a week, and then for molar neck bone mineral density for the sample of the 15 moment. The data were collected through the prospective cohort study. So I put the table in here, say number of the Coca-Cola per week, and then this is actually the people, and that's the density. All right, so if you actually figured it out with this two data as the correlation between number of cola per week and the bone density, R is negative 0.806, okay? So you can figure it out there using the previously the R formula, okay? And then the critical value from the table 2 which is 0.514. Okay, so now compare, but we need to use R as absolute value, okay, which is a negative 0.806, which is still greater than 0.514, but this time is actually the negative. So we can still say yes, it is a linear relation. Okay. All right. But it's a negative relation because R is a negative. All right, so we have a more, actually, put that thing here too. There's a table continue. All right, so this sections we talk about the linear correlation. Thank you for listening.